Hello everyone, welcome back to the latest lecture session. In the last session, we looked at coagulation and the relevant principles involved in destabilizing the particles or the solution. Let's get right into it. So, we are in the context of water treatment, we want to remove the suspended solids. Yes, some of these solids, colloids, too small, they won't settle down. So, we want to bring them together so that they form a bigger particle or a flock so that we can settle them down. Why won't they come together? We looked at this net negative charge on the particle, right, and it attracts counter ions which are cations. That's what we see out here. Negative charge on the particle, we looked at the relevant reasons and so on and so forth. And we know that the repulsion is something like this and the attractive force is something like this. And the net, I guess, is something like this, right. So, as the particle, this is distance, the x-axis is distance. As another particle approaches our particle of interest, it has to overcome this maximum. How do we, see to it that these particles can come together? We need to suppress the repulsion forces or forces of electrostatic force of repulsion. And how do I do it? By suppressing this electrical double layer or this, right, or more importantly this diffuse layer, let's say, right. So, that is what I can do. And how do I do that? I can increase the ionic strength. Ionic strength, as we know, will depend upon the charge to the power of 2, and this is how it is. And obviously, it will also have the concentration. So, concentration, I will write it as this Ci, Zi, right, I equal to 1 to n. So, summation of all the ions, this is I equal to 1. So, what does this ionic strength depend upon? Obviously, the charge of the relevant ion. Let us say if it is Na plus, so plus 1 charge. If it is Ca2 plus, 2 square 4, right. And Ci is the concentration of the relevant element, let us say Na plus or Ca2 plus. So, that is how you have ionic strength. Yes, and we looked at different ways to compress this or decrease the thickness of this electrical double layer. And what were the primary aspects? Okay, let me see where I can write that down. So, the primary ways were charge neutralization by adding or increasing the ionic strength. And in that context, we saw that if we add counter ions or increase the ionic strength by adding ions that are bivalent or trivalent, we saw that charge density is relatively higher. The effect on the ionic strength is multiplied. Again, we see that here also Z square, and I think we also mentioned this 1 square is to 1 is to 2 square is to 1 is to 3 square. I mean, or charge, I guess, not square, pardon me, to the power of 6. Right. This will give you an idea about the concentration that is required if it is monovalent, bivalent, trivalent. Trivalent, that is why 3 charge, bi, that is why 2, mono, that is why 1, I guess, right. So, you see that with respect to, let me rewrite this here in a clearer manner. So, if it is only 1 charge and if it is bivalent and if it is tri, I guess, right. So, as you see with higher charge, lesser concentrations need to be added to have the same effect as, let us say, monovalent one at relatively high concentrations, and we see the ratio that they need to be added at. This is in theory anyway, and more or less what we observe will also closely follow this relationship, unless NOM, there is too much NOM. Again, let us come back to this. So, charge neutralization, this is how we can do that by increasing the ionic strength. So, adsorption and charge neutralization go hand in hand. And in that context, we also looked at another aspect, I guess, at least we looked at sweep coagulation, or at least I think we would have broached upon it, right. As in, I have a metal that I am adding and I have ligands which are electron rich, let us say OH minus or any other ligands, right. And where the critical concentration, you are going to have precipitation of these metal hydroxides, or what do we see, insoluble metals at that levels, metals which are insoluble at that concentrations of the metals and ligands, right. You will have them precipitating up. So when you are precipitating something out from the solution, right, it's not dissolved anymore, it's in a different phase, it's a solid phase. So these can absorb, what do we say, the other particles of interest or colloids, right, or will provide sites for adsorption, and they will settle out. So that's called sweep coagulation or co-precipitation. It's also called co-precipitation. In though strictly speaking, it's you are not precipitating the other colloids out, you are just giving surface area for them to adsorb onto. And the third aspect is, I think we looked at the picture, interparticle bridging, right. So interparticle bridging. So these are the ways you can bring about coagulation or destabilize the system. Interparticle bridging, I think it's self-explanatory. You have a particle here, my polymer or such is adsorbed here, and the other end or the other multiple ends, they can adsorb onto other colloids. So I am going to form a bridge, right. And in this context, we are in the context of charge neutralization by adding the relevant or adding ions such that the ionic strength increases. So here, first we see that if it's with increasing concentration, obviously ionic strength is going to increase, yes, and thus the relevant electrical double layer is going to decrease, right. Again, ionic strength, it's going to be depend certainly on the charge, right, and also the concentration of the relevant compound. As you see, though, charge has a greater role, and let's see that. So compare, let's take this set and this charge, electrical double layer, 3, much lesser, let's say, right. So that's something to keep in mind, yes. So let's move on. And in the context of adsorption and charge neutralization, we see that Al3 plus and Fe3 plus are quite commonly used. But here it's not only charge neutralization, that's something that we discussed, and I think I will come back to that later. We know that any Al3 plus that is added will not stay only as Al3 plus in solution. That's the key aspect. So it won't stay as a free metal, it will transform, but we will look at that later. Again, even that's the same case with Fe3 plus, right. So what is it that we are discussing here? So it can reduce the negative charge associated with the particles, as in we know that NOM will impart the negative charge to some of these colloids, and that's why they can't come together. NOM being a ligand can, what do we say, form a complex with this Al3 plus or Fe3 plus, thereby bringing down the charge on the relevant particle. So that's one aspect, but we'll come back to this aspect of Al3 plus, transforming into other, what do we say, compounds or forms. Okay, I guess this is where I wanted to discuss this. So whenever I add a metal, right, let's say a source of Al3 plus, alum or any other sources, what would I want it to be? I want the reactants to be such that finally I have Al3 plus. So that's pretty good. I increase the ionic strength and the electrical double layer thickness decreases, but it's not as straightforward as that. Al3 plus will not stay only as the free metal. Let's say this is what I am calling as the free metal. It will be in equilibrium, right? It will be in equilibrium, let's say, with different complexes. The different complexes will be formed when you have a metal and a ligand. And the most common ligand out there is OH minus, right? OH minus. So Al3 plus can form ligands with OH minus. This will be in equilibrium, right? So Al OH 2 plus. You see now that the charge is no more 3 plus. Again, if I have, let's say, depending on the concentration of OH minus, I can even have this complex being formed, and you see now it even has a negative charge. And more importantly, as I mentioned, depending on the conditions, we will look at the graphs that will give you an idea about that. So Al3 plus with a ligand can form complexes, right. So that's one aspect to keep in mind. Al3 plus, which is the free metal, will be in equilibrium with complexes. For that you obviously need a ligand, and the ligand is NOM also, but that helps us in a way. And another aspect is it can even form a solid. Solid meaning it's not dissolved in the solution anymore, right. So Al3 plus 3 OH minus can lead to formation of AlOH thrice the solid. It can also lead to formation of AlOH thrice the complex with no charge, but it depends on the conditions again. So, if Al3 plus concentration is high enough and pH is also high enough, you will have a lot of alum precipitating out of the solution as a solid. So, two ways, one can be complex formation with NOM, Al3 plus forming a complex with NOM and neutralizing the charge on the particle. But obviously, you will also have to look at Al3 plus forming a complex with OH minus, and then charge neutralization, the effect will decrease, as you can see. And another aspect is that Al3 plus can precipitate out as a solid, and while precipitating out as a solid, as we mentioned, it can lead to co-precipitation. It can act as sites where the colloids can adsorb, or this is also called as sweep coagulation, right. So, this is the thing, and again please note that they are in balance, right. Depends on, it is like this, more Al3 plus, then this precipitation will take place. So, it is a balance, yes, and the balance is between the free metal, the complexes, and also the precipitate here, let us say, right. So, that is something to keep in mind. And same thing will happen with solids like solids, metals like Fe3 plus and such. Not a lot for Fe2 plus. Fe2 plus is very much soluble, mostly stays as the free metal itself, but Fe3 plus will form a lot of complexes and will also precipitate out. Again, so that is why you need to be careful about what you are choosing. Let us move on. So, this was a good schematic we looked at. One case was correct mixing and excessive mixing, which also plays a role. We will come back to that. So, here what do we see? We see the polymer being added and the stable particles which do not want to come together. Now, the particles are stabilized after the relevant polymer has adsorbed onto the particle and neutralized some of the charge in a way, if it is cationic. If not, it has adsorbed it, yes, and now it is forming a bridge, right, by bridging two or more particles. So, now you have a good flock particle. When you have excessive, again that is not good, we will look at it depending on the charge, that will lead to issues. It can even stabilize the system. And another aspect is due to poor mixing, let us say, what will happen, this end which should have adsorbed onto the other particle is now readsorbed onto the, not readsorbed, adsorbed onto the same particle, and it has restabilized, let us say. Again this I do not want, and if I mix it way too much during flocculation, again this phase is coagulation maybe, and this phase here I guess is flocculation. So, here I want a lot of mixing and here I do not want a lot of mixing, right. If I mix it a lot here, what is going to happen, the flock which was in this stage is going to break up, right, if I mix it way too much or I mix it for way too long. So, there are these aspects which we will look at. So, we need to be conscious of how much energy we are imparting to the relevant solution from our paddles or such, how much mixing I am imparting to the relevant or how much turbulence I am imparting to the relevant solution. Let us keep that in mind and move on. So, as I mentioned, it can be enmeshed in a precipitate and it is called sweep coagulation, typically seen with Al3 plus and Fe3 plus, not with Fe2 plus though, typically seen with Al3 plus and Fe3 plus and not with Fe2 plus though, right. So, this is I guess a general schematic. You have, hopefully this is the precipitate, Al3 plus AlOH thrice solid, AlOH thrice the solid, and you see the different colloids being enmeshed in that particular solid, let us say, right. So, that is one aspect to consider. And as I mentioned, if we add too much of the polymer, especially a charged polymer, it can lead to, what do we say, reverse stability, if I may say so, but that is a term that I am using. Let us look at it. Here what do we have? Let us look at this graph first. Polymer adsorbed onto the particles, or how much I am adding I guess. Okay. Polymer dosage is given, polymer adsorbed is given. Not all of it will be adsorbed, so some of it will be adsorbed. So, you see that after certain dosage, with increasing polymer dosage, adsorption is not increasing. So, there are no more adsorbable sites or sites for adsorption. So, there is one threshold even for adsorption, that is one thing to keep in mind, right. And the other thing, let us say, is that, let us look at this ultraphoretic mobility, let us say, right. which was looking at or will give you an idea about the potential, if I may say so. Fine. So, initially it is negative and I want to decrease this by adding the cationic polymer, I am decreasing it, right. But then due to excessive addition, from I guess 0.3 or so, I now see to it that it is positive, 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 and now what was stable because of net negative charge, I am now making them stable because of positive charge, if I may say so, and then obviously the relevant profile. So, that will be very much clearly illustrated in this figure. So, in this zone what do we see? It is negative. So, if I add alum, it is going to be a sharp decrease, as in I am going to decrease the thickness of the electrical double layer by increasing the ionic strength. So, there the particles can come together and I see that the turbidity is decreasing a lot, right. Turbidity is giving me an idea about the suspended solids, right, and it is decreasing. So, it stays the same. So, here it looks like it is the optimum dose here or here, depending upon to which extent you want to remove the turbidity. But as I keep adding, now the particles are becoming relatively more stable, or even the cation itself can act as light scattering agent. So, you see that turbidity is increasing and you see that that mirrors considerably with respect to this profile out here, and then you see that it results in a maximum here, I guess, right. So, that is one aspect to keep in mind. So, excessive addition of the polymer too will lead to issues. So, there is a sweet spot with respect to the amount and the costs and the turbidity that you want to capture. Let us move on. So, typical coagulant, we say alum. So, it looks like this is what we have. We have a source of aluminum. So, you can't have any solid that has charge. So, obviously, you are going to have the anion, so that there is net zero charge, and obviously it is hydrated, let us say, right. Al3 plus and SO4 2 minus, right. So, that is why it is Al2 SO4 thrice, let us say, right. So, 6 charge, 6 charge, okay, that is fine, but we know that Al3 plus does not stay. Once we add this, let us see what happens to the solution. It will dissociate once I add it to the water, or dissolution, if I may say so, maybe dissolution, dissociation or dissolution. So, what is it going to dissociate into? So, obviously Al3 plus and SO4 2 minus, mind the stoichiometric coefficients, Al2, so 2 Al3 plus, SO4 3, so 3 SO4, and charge is 2 minus, and water, I guess, right. So, this is what we have, but do we know more, as in Al3 plus won't stay only as Al3 plus, it can be, not it can, it will be in equilibrium with the complex. This is the free metal, and also as a solid, let us say, right. It will be in equilibrium with these three, between these three forms, let us say, right. So, let us see what else we have here. Okay, Al3 plus itself can neutralize the charge on colloids, but we know that might not happen depending upon the level of complexes and type of complexes being formed. And if this happens, or part of it or some of it will happen, it will, or could rather, compress the double layer, right. But as we discussed, it can form complexes, and even these complexes can neutralize some charge, let us say, right. But if primary motivation is only charge neutralization, you see that if I add Al3 plus, the charge that I am getting, let us say, it is not going to be 3 plus anymore, right, because I have OH minus that is forming a complex with my metal, let us say. That is one thing to keep in mind. But what else happens? You have the solid being formed, formation of solid hydroxide. So, this is what happens. So, this will precipitate out, and we know that sweep coagulation or co-precipitation occurs. So, though we discussed it earlier, we just want to mention the relevant equations and such. In general, you do not need to mug them up, but standard equations or simpler equations like this, one would expect you to be able to come up with it, right. I want AlOH thrice solid from Al3 plus, I know I need to add water, or you can see to it that rather than releasing H plus, you can add OH minus, it depends. But in the exam, some of these equations you should be able to come up with them, right. Depending on the OH minus and Al3 plus concentration, most of the aluminum or Al3 plus can form a solid, let us say, or can precipitate out. That is something to keep in mind. Okay, alkalinity requirement. First, what is this alkalinity about? Let us just understand one aspect. So, with increasing carbon dioxide emissions, right, you have a lot of carbon dioxide in the gaseous phase, right. But if we are able to capture all the emissions and measure or quantify them and look at the carbon dioxide concentration in the gaseous phase, you will get a relatively lower value than expected. Why is that? Because you have these oceans, vast area, right, and considerable mass of water is there. So, carbon dioxide in the gaseous phase will be in equilibrium with, or it will dissolve into carbon dioxide in the aqueous phase or water, right. It will dissolve, and this will then further transform into H2CO3, the acid, which will be in equilibrium with the other deprotonated forms, which are HCO3 minus and CO3 2 minus. So, you see it is an equilibrium again, and in this context we looked at pH, pKa, right. We looked at that earlier, we might look at it again. So, why I mention this is, as you see, in general in the water we will have HCO3 minus and CO3 2 minus, and also due to the lime deposits and such, you will have CO3 2 minus, or lime that is in or the deposits will act as a source of CO3 2 minus. So, you will have carbonates in our water, a lot of carbonates in our water. Why are they important? Well, one aspect is as you add an acid to water or any natural water, you do not want the pH to drop. Why? pH will affect life. We can't drink pH or water that is at 6 or such, for a prolonged period of time. Please do note that the what is this, carbonated drinks like Pepsi, Coca-Cola and such have remarkably low pH, I think 3, maybe 4, I guess. And obviously you can't keep drinking them for a prolonged period, right. First you will have the issues with teeth, and then with respect to your system. Again, human body, yes, issues, and life in general too, it will not survive when the pH is low. So, this alkalinity of a solution will prevent decrease in pH, or will resist the decrease in pH. What will it do? It will resist decrease in pH, decrease in pH. And how will it do that? Let us understand that. When we say decrease in pH, what do we mean? We know that pH is equal to minus log activity or concentration of H plus. In this class, we are going to assume activity is equal to or approximately equal to concentration. This is the what do we say, these brackets, curved brackets we use for activity, but discussion about activity is beyond this course, and these brackets we use to denote concentration. Okay. Anyway, so how is that pH will decrease? The pH will decrease when we increase the H plus. You can see that obviously from this relationship. So, how will H plus increase, or when will it increase? It will increase obviously when I am adding a source of H plus. What are the typical sources of H plus? It can be an acid. I know that HCl, strong acid, because pK is very low. At most pH ranges, it will go to H plus and Cl minus, or there are other acids too, which are relatively weaker, acetic acid, let us say, right. Acetate and H plus. So, when I add acids, depending on how strong, for example, this is strong acid, pK is 0 or less than 0. So, it will always release H plus at almost all the pH ranges. This is not such a strong acid, the pK is 4.76, right. So, we looked at this graph if you remember, right, and this is acetic acid. I will say it is HAC, HAC. This I am representing by HAC, this by AC minus, and let me just change the color here, and the other one will be AC minus, right. I am just reviewing the acid base relevant aspects, and this one, the point at which HAC and AC minus will be the same is the pKa 4.76, that is the pKa. Why is this relevant? As you can see, when the pH, this x-axis is pH, y-axis is relative concentration of the relevant acid or the base, right. As you see, when the pH is less than pKa, which form is predominant? The protonated form, HAAC, right. This is predominant. But when this is predominant, will it be able to release the H plus? No, it cannot, so it won't affect the pH. But if the pH of the solution is greater than 4.76, and then if I add acetic acid, you see that acetic acid will dissociate and form AC minus. That is what we see. Let us say, for example, at this case, any acetic acid that I add mostly will dissociate to AC minus, and only some will stay as HAAC. So, most of it will dissociate and considerable H plus will be given out, and thus you can change the pH or affect the pH. So, that is what we need to be concerned about, the pKa and pH of the solution. So, coming back to where we were. So, in such a way, different acids or process can lead to increase in H plus. When H plus increases, obviously pH will decrease. This I do not want. But nature, obviously our friend, always tries to help us out. So, let us see how it does it. So, either with equilibrium with carbon dioxide gas and then the relevant compounds, which we call the carbonate system, or more importantly the limestone deposits in the land or subsurface, they are going to see to it that you have considerable carbonates in the system, right. Carbonates, yes, inorganic forms of carbon. Why are they important? Let us see. For example, I have HCO3 minus in my solution, fine, and if I add the H plus from any other acid, let us say I add HCl to water and that goes to H plus and Cl minus. If there is nothing else, this H plus will then add to the other H plus that is already there, H plus concentration will increase, then pH will decrease, right. That is the usual way. But if I have HCO3 minus, what will it do? After this addition of HCl, H plus is released, fine, but that H plus now will be taken up by this HCO3 minus. So, H plus HCO3 minus will go to H2CO3, right. So, you see this H plus is taken up by this base, and this H plus does not exist as free H plus. So, it can't affect the pH, but that depends upon how much H plus is being added and how much HCO3 minus is there and what is the pH, and thus the pKa relevant aspects come into play. Same case, if I have CO3 2 minus in my solution, it can take up H plus and go to HCO3 minus, right, or it can even take 2 H plus, right, and go to H2OCO3 and such, let us see, right. So, these aspects or these carbonate system play a life sustaining role, right. They act as agents that will resist the decrease in pH, right. So, that is what it is. So, let us see what this equation for alkalinity is. Okay, let me write it here. Equation for alkalinity in general, okay, there will be other variations, but in general. So, what is it going to be depend upon? It is going to be depend upon the bases that are usually present in water. What are the bases present in water? Obviously, always OH minus, and depending on the system in nature, you will always have HCO3 minus and CO3 2 minus, right. Since CO3 2 minus can neutralize 2 H plus, right, you see this here, you will have 2, that is the equivalents, let us say, and obviously OH minus, so I have to subtract H plus. So, this is the theoretical definition of alkalinity. So, without alkalinity, right, in general, if pH is near about 6 or 7, OH minus and H plus will cancel out, CO3 2 minus will be negligible, and mostly we are concerned with HCO3 minus. But if there is little to no alkalinity and any acid is added, because as you see when you are adding alum, acid was being released, right. So, 3 H plus is being given out. Let me see if even the other reactions, even when the complexes are being formed, H plus is being released, right. So, you see that H plus is being released into the solution. So, without medium bases to neutralize or take up this H plus, what will happen? The H plus will affect the or add to the H plus already there. It will increase the H plus, decrease the pH, which you do not want, right. It will affect our engineering aspects as in the pipes and such, and also affect life. So, you do not want that. So, in general, you want to maintain sufficient alkalinity, let us say. So, right, that is the background. but I am out of time. We will continue this in the next session. Thank you.